In this lesson, we're going to learn about the derivative. Now, the derivative is one of the most important concepts of differential calculus. So basically, when you think about calculus, there are two different areas of calculus that we study: differential calculus and then integral calculus. The first half of this semester is going to be differential. Then we're going to transition into integral calculus, and they are related, which we're going to see later on. However, let's focus on the derivative right now. So the derivative tells us how fast the dependent variable is changing with respect to an independent variable. Now, this independent variable, sometimes we label it as x. So let me just go ahead and write this down. So the independent variable, sometimes we label it x, but a very popular variable is going to be time. Because what we're really concerned with is how fast is something changing with respect to time. This could be things like how fast is your money growing in your bank account. That's always important. We might also be concerned with how fast the population growth is of wolves, because they may be eating bunnies or something like that. We might be concerned with how fast is an object moving through a magnetic field. Okay, all these, anytime you say the words how fast, we should be thinking differential calculus. So I think a good place to start is right there. So let's recall, and we did problems similar to this back in chapter 2. So to recall that, if s of t is the position of the object at time t, then the average velocity of the object over the time interval from a to t is so the average velocity is going to be equal to s of t minus s at a, all divided by t minus a. In other words, it's just the slope of the secant line, which we've seen a bunch of times. The derivative is what we call the instantaneous velocity. At t equals a. In other words, what we're saying here is this. With the average velocity, you need 2 points. And earlier I gave a nice little demonstration of how to calculate different secant lines, and we noticed that as the step size got smaller and smaller and smaller of some function. So let me go ahead and exaggerate this here. So here's a point and here's a point. Here's our secant line. But we found that as we allow this 0.2 to get closer and closer and closer to 0.1, we found that our values of the slope started to converge to some specific value. Okay, and we were estimating what that value would be based off maybe a table or something like that. Well, now we're going to take this concept of the average velocity, and we're gonna integrate that with our concept of the limit. So the derivative is the instantaneous velocity at t equals t equals a, as t approaches a. So that is given by this. So we have the velocity, or the instantaneous velocity, is going to equal the limit as t approaches a of s of t minus s of a, all divided by t minus a. All right? And that is what we call our slope of the tangent line. The word tangent is Latin, and it stands for touches. So what we're really trying to find here is the slope of the tangent line, or better yet, the equation of the tangent line, which we're going to do a lot of. We're going to find the equation of the tangent line, and this line only touches our function once. It just skims it and hits it once at some specific value. So I think the easiest way to kind of demonstrate this is to go ahead and let's do an example. Okay, so for the first example, we have a rock is thrown upward on the planet Mars. The height in meters, t seconds later, is given by y of t equals negative 16t squared plus 100t. So the first thing we're going to do is find the average velocity over the time intervals. The star means I'm going to do the first one by hand, but then the intervals 1 to 1.01 and then 1 to 1.001 I'm going to do using Excel. It just makes my life a little bit easier in terms of calculations. Part B, we're going to find the instantaneous velocity when t equals 1, and you're going to see that there's a relationship between parts A and B. 3, we're going to actually find the equation of the tangent line when t equals 1. And remember, that equation line, that tangent line, will touch our function exactly one time at t equals 1. And then just to demonstrate that, I'm going to go ahead and graph both models to show how that works. So with the first one, let's start that off. So we know the function is y of t equals negative 16t squared plus 100t. Now recall that the average velocity is going to equal, well, in this case, it's going to be y of t2 minus y of t1 all over t2 minus t1, where t1 and t2 are going to be the time intervals. So I think the easiest thing to do here is just to kind of break it up a little bit and say, okay, well, y of 2 is going to equal negative 16 times 2 to the second power plus 100 times 2. So if you just want to give me a second here, I'm going to do that on my calculator real quick. Yes, I'm lazy. I use my calculator all the time. I've done enough mental math in my life. So we get y of 2 equals 136. And then the second part is going to be y of 1. All right, and that's going to be negative 16 times 1 to the second power plus 100, or just negative 16 plus 100, which is 84. And I'm just going to substitute those values into my average velocity equation. So I get 136 minus 84 all over 2 minus 1, and 136 minus 84 is going to be 52 over 1, which the average velocity is going to be 52 meters per second. Because remember, this is the object. It gave us, well, meters. Yeah, the height was meters, t seconds later. So meters per second. All right. Now, like I said, for the other two, I'm just going to go ahead and use Excel. So here I already kind of have it typed up and everything. We have our initial time. We have our final time. For the interval 1 to 2, we found that the average velocity is 52 meters per second. I am very weird with Excel. I like everything to look nice and neat. So pardon. I'm just going to center everything and then bold this because that's what I like to do. Now, to find the other intervals, notice that from 1 to 2, it's 52 meters per second. From 1 to 1.01, 67.8. From 1 to 1.001, it's 67.9. And then even if I got even closer, I see that it's 67.999984. In other words, this is getting so close. And if I were to round this number to the nearest whole number, I would say it's 68 meters per second. So what I'm going to do here, let me see if I can do this. Can I just copy and paste this? Boy, that'd be nice if I could just copy and paste this into OneNote. Oh, look at that. That's beautiful. Beautiful. I love it. Yeah, it's good enough for me. Okay? So here are this is all part A. Now, part B wants us to find the instantaneous velocity. So find the instantaneous velocity when t equals 1. So if we use the equation that we gave earlier, okay, we know that the instantaneous velocity, I'm just going to abbreviate it with v sub int. I think that's good enough for us. So the instantaneous velocity is given by the limit as t goes to, well, in this case, it's going to be 1 of y of t minus y of 1, all divided by t minus 1. Because remember, a in this situation is 1. Okay? Now, in part A, we learned that y of 1 was equal to 84. So what I can do up here in my instantaneous formula is I'm just going to write the limit as t goes to 1 of y of t minus 84 all over t minus 1. So now I'm going to go ahead and make my substitution. We know that y of t equaled negative 16t squared plus 100t. So I'm going to make that substitution. So my instantaneous velocity is going to equal the limit as t goes to 1 of, and I'm a big fan of using like parentheses and brackets, so I'm going to put a bracket first. Negative 16 t squared plus 100t minus bracket 84 all over t minus 1, which gives me the limit as t goes to 1 of, and now since I can go ahead and distribute if I have to. The number one mistake students will make is that little minus sign. They won't distribute it to the second part of this formula if you didn't simplify it initially. So just be extremely careful. That's why I put brackets around and parentheses around any type of substitution I make. So this is just going to give me in the numerator negative 16 t squared plus 100t minus 84 all over t minus 1. Okay, now, we know right from here, if I were to take my limit and substitute it in, I would get 1 minus 1 in my denominator, and then this whole thing would just be for nothing, because it would be undefined. So what we're going to have to do is we're going to have to do some sort of algebraic manipulation here, okay? So what I'm going to do is I'm going to factor the numerator, and the numerator factors down into negative 4 times the quantity t minus 1 times the quantity 4t minus 21. Now, if you need me to show you how I did that, please send me an email so I can show you, okay? Or better yet, maybe I'll just make another video and show you how I factored that. Because all I did was factor out a GCF and then complete the square. Okay? Now from here, I'll put that in parentheses, we can see that the t minus 1 in the numerator, t minus 1 in my denominator, they reduce. So I can scratch these out. Just clean it up here a little bit. That gives me negative 4 times 4t minus 21. And now I can go ahead and make my substitution. So this is going to give me negative 4 times 4 minus 21. 4 minus 21 is going to be negative 17. And then 4 times negative 17 is positive 68 meters per second. So you can see, and I'm going to scroll up here a little bit. when finding the average velocity, we noticed that our values were getting closer and closer and closer and closer to 68 if we were to round it to a nearest whole number. Using the instantaneous velocity formula, we calculated that at t equals 1, the instantaneous velocity is 68 meters per second. So there's part B. Now part C said, let's go ahead and find the equation of the tangent line at t equals 1. Okay, so anytime, and I'm going to highlight this, anytime you see the words, find the equation of the tangent line, you need to be thinking two things. You got to be thinking, one, you need the slope, and two, you need a point. Now, back in algebra class, you did tons of problems like this where it was like, find the equation of a line. Find the equation of a line parallel to, or find the equation of a line perpendicular to. Regardless, you've seen the words, find the equation of the line. Now, the slope in algebra was y2 minus y1 over x2 minus x1. We know that. But in calculus class, this slope is now going to be our derivative. Because remember, the derivative measures the instantaneous rate of change. It is the slope of the tangent line. It measures how fast is one variable changing with respect to another variable. The point is just going to be the point a comma f of a. Well, in our case here, we're concerned with t equals 1. So in order for us to find this point, we need to evaluate y of 1. Well, we already know from earlier, our point is going to be 1 comma 84. So I have my derivative, check. I have my point, check. I can find the equation of the tangent line here. Now, we're going to use the point slope form of a line to find our tangent line. So, if you don't remember this is going to be y minus y1 equals the slope. Now, here's the thing. In our case, this is going to be the derivative. So for now, all right, I'm just going to write the word derivative. Later on, I'm going to use the actual notation of the derivative. So this is just y minus y1 equals our derivative times the quantity x minus x1. So we get y minus 84 equals 68 times x minus 1. That's going to give me y minus 84 equals 68x minus 68. And then just by adding 84 to both sides, I get y equals 68x plus 16. And there is our equation of the tangent line. That's a horrible looking error. Let's fix that. Now, if we've done everything correctly, we can go into Desmos. We're going to graph the model. We're going to graph our tangent line. And this line right here that we just found, this line should touch at 1 comma 84, and it's only going to touch once. So let's see how that works. So here we go. Let's start typing everything in. Now, I want you to notice my window. I already kind of fixed my window so everything would look good. So we got negative 16t. Where is my keyboard? I have like 8 keyboards in front of me. It's ridiculous. All right, I got my keyboard. Sorry. So we have negative 16. Now, in Desmos, you got to use the letter x instead of t. So negative 16 x to the second plus 100x. So here's our model, okay? And it makes sense. I mean, if you think about, regardless of what planet you're on, if you throw an object up in the air, gravity is going to pull it back down. So we can see that this goes up and then it goes back down. Now for our equation of the tangent line, we got y equals 68 x plus 16. And notice right here, and I'm going to click on it. Help me out. There we go, right there. At 1,84, that's where we touch it exactly one time. I can zoom in. And that's actually not that good of a zoom, but you get the point. There it is. That's what I wanted. See, once you zoom in enough on Desmos, it will actually tell you where did you cross. And now I'm just going to zoom out. See if it'll do it again for me. There we go. So that's the point at which that tangent line touches exactly once. And that gives us tons of information. Right here I can see that not only is the object going up, but the velocity is it's very steep, which means it's moving pretty fast. Now, if I zoom out here, you're going to see what happens. If you think about all the little tangent lines, let me copy this into our notes. So I just want to drive this point home. I think I need a new laptop. I think I said that last video, but that's okay. All right, here we go. So part D, and let me just hit Control Paste. There we go. So this is the point right here, 1,84, somewhere down here where it touches only once. What I'm really concerned with now is, notice that if I were to draw like a tangent line right here, that's what it would look like. If I were to draw one right here, that's what it would look like. And the most important one, honestly, is right here. Okay? We can visually see that the slopes of the tangent lines are starting to decrease. They're getting smaller the higher the object gets, and then gravity kicks in and it pulls it back down. Now, at this point right here, not only is that the max height, but at this point, my instantaneous rate of change is going to equal 0. And that's the point at which the rock reaches its highest point on Mars. Then gravity kicks in and it starts pulling it back down again. Okay? So that's what we're talking about here when we talk about like instantaneous velocity and how this relates to just the basic concept of where's the rock at. In algebra, we were just concerned with where's the rock. Or maybe we were concerned with when does the rock hit the ground? You know, how many seconds? If I go back to the graph here, the rock is going to hit the ground at 6.25 seconds. All right? In calculus class, we're concerned with how fast is the height changing as time keeps increasing? Or at what time not only does the rock reach its highest point, but where does the velocity change? When does gravity really start to just pull the rock back down? Because as soon as you throw the rock up in the air, gravity's already working against it. Eventually, gravity is going to win. Where does that happen? All right, so I hope that makes sense. This is a very simple example. Actually, if you go to any calculus book and you go to the section where it talks about derivatives, this is just called the velocity problem. It's a very famous problem, and I think it's a really easy problem to kind of wrap your head around, the idea of a derivative and how it relates to everything that we do. So I hope this video helped, and I'll see you in the next example.